So here I have summarized all the results that we have obtained so far. Okay, so here is the formula for the S matrix. Okay, and this contains the Fourier transform of the Green's function g tilde m plus n, and then we also analyzed what g tilde n is, and we saw that in general we can write it as a product of 2-point functions, okay, g tilde 2 q1 to g tilde 2 qn, so for each leg, times the amputated Green's function, okay, where this g tilde of q I had defined here. Okay, so this is Green's function in the coordinate space, and then you take a Fourier transform, and g tilde q is related to g tilde 2 q prime by this relation. Okay, and that is what we had seen last time. And then I also made a claim that if you look at g tilde q, g tilde 2 q, this object, okay, which we are going to do later, that we will show that it has a structure which is almost the same as that of a free propagator. So if you had a free theory in which the particles had mass mp, then you would have had I over p square. Okay, this should be q because I'm using a q here. I over q square minus mp square plus I epsilon. Okay, but now the difference is that you also have a factor of z. Okay, and then other terms which are not singular in q square going to becoming equal to mp square. Okay, so that's the difference, but this is almost like what you would have in free theory as far as this term is concerned. Okay, so before we take up this function in a non-perturbative manner, let us assume that this result is, let's just take this result and analyze this object in a perturbative manner. Okay, so that's the plan. Okay, so let's see. So we look at g tilde 2 q or p, whatever you like, in perturbation theory. Okay, so here this is 2-point function. Okay, when I put a blob like this, a shaded blob, then this is a 2-point function, or rather g tilde 2 or g tilde with one argument q. Okay, this is a 2-point function, but this has two arguments, this has only one argument, and right now I'm just denoting that blob. That blob denotes g tilde 2 with one argument. Okay, this is what it is. And we saw that for 5-4 theory, this is sum of all these terms, all these diagrams. This is order lambda diagram because you have one vertex. This is order lambda square diagram. Okay, you have such diagrams and many more, and still more. You have this also at order lambda square. Okay, this at order lambda cube, and so forth. And of course, you also have terms of this form. Okay, there are infinite number of diagrams and I'm just showing some of these. Diagrams of these kind, these are called one particle, these are called one particle irreducible diagrams. Okay. So let's look at this one. This one is not a one particle irreducible diagram. Why? Because if you cut this line here, if you cut it with a scissor, this falls apart into two diagrams. Similarly here, okay. So these are reducible. You can cut and they will fall into two. But here, there is no single line which you can cut and you get two diagrams. Okay. So the thing is that you should be able to, upon cutting one line, you should be able to get two or more diagrams, or two diagrams, then it is reducible, otherwise it is irreducible. So these ones, these first three are irreducible, okay, these ones are reducible, because here also you can cut this line, you get two, or you can cut here, you again get two diagrams. Okay. So one particle irreducible diagram is a diagram that does not split into two diagrams by cutting a single line. Okay, so now let's look at these irreducible diagrams. I will define one particle irreducible diagrams. So by this blob with one pi written in it, I mean the collection of all one particle irreducible diagrams. Okay, so you have this plus this plus and so forth. Okay, there are infinite of them. So this blob will denote this. Okay, but remember, when I am drawing one pi, okay, these lines, this one and this one, okay, there is no propagator factor for this. So when you draw this, for example, when you draw this one, you don't write a propagator for this and a propagator for that. You just write what you get from this loop. Similarly here, you do not write anything for these two ends, but only what you get from this loop, these two loops. Okay, and so forth. So these two lines, okay, these two lines you never include in one pi. Okay, so that's the definition. And I will denote this by I times sigma. So here is q entering into it, I times sigma of q square. Okay. So you see, whatever happens here, whatever function you have, this integral, you'll have a one loop integral here, here you will have a two loop integral. Okay. All those, that function which you get here will be a function only of q square. Right, because that q enters into this loop, and then other things are just dummy variables. I mean, other loop integrals are going to be completely integrated over, and what will be left behind is a function of q square. Okay, and that is what I am emphasizing by writing I times sigma of q square. Okay, why I have chosen a factor of I here, you will see the relevance of it. But that's a definition. I'm just going to denote it by like this. Okay, so that's fine. And remember that sigma of q square, I times sigma of q square, which is this one particle irreducible diagrams, the sum of them is a function of q square will also be a function of m square and lambda, right? So sigma q square is a function of q square, m square and lambda, right? Because these are the parameter, m square and lambda are the parameters that enter into your calculations. So of course it is going to depend on all of these, but I am going to suppress m square and lambda and just write q square, only q square. Okay, now it is clear that if you look at the 2-point function, okay, this object, I should have put a 2 here, a superscript 2, and this says what? This is first just a propagator, so I write a propagator, plus this, plus this, plus this, and all other one particle irreducible diagrams. So let's say first row has all those irreducible diagrams. So it will have, okay, and so when I write this, I have to include I sigma q square for this, but now remember I am writing a 2-point function, so these two propagators are part of it. So here I write propagator for this, and here I write propagator here, propagator there, and then 1 pi is only minus I sigma q square, okay. So in this expression, in this line, I have to include propagators, okay. But here it is defined one particle irreducible diagram, they are defined without the propagators. Okay, so what else? Now let's look at this one. You will have this variety. Let me include one more diagram. Okay, and others. So you see this one will have a structure of the following form. Right? Here, if you cut this line, it falls into 2, and this is how these diagrams are. Then of course you'll have, and so forth. Okay. So let's write it down. You have momentum q flowing into it. So this will give you a factor of a propagator. That gives you a propagator. This will give you a propagator times a sigma, I sigma times a propagator. Okay. So a factor of sigma and a propagator here. Similarly, a factor of sigma, a propagator here, a factor of sigma, a propagator here. So 2 sigmas, 2 propagators, and then 1 additional propagator from this. And here 3 sigmas, 3 propagators, and an additional propagator from here. So the structure is the following. Each of them gives not MP. Did I write MP before? No. Okay, this is not the physical mass. This is the parameter in your theory. Remember, that's this propagator I am writing. Okay. So here, each of them has one propagator which is on the left. That is what I am taking out. Okay, I am factoring out. And then you have 1 plus I sigma q square times a propagator which is on the right plus so you have 2 factors of these. So I have already taken this one common, factored it out. Now you have 2 factors of sigma. They both have the same q square entering into them. And then these 2 propagators, which are again identical. So I write this. Okay, and remember this is m square, not physical mass. Okay, so that's the series you have, and you know that this we can sum up. So this has a form of 1 plus x square and so forth. Okay, remember sigma is a function of lambda, and actually it starts at order lambda because this is the first diagram and the diagram appears at order lambda. So sigma has a perturbative expansion, and the expansion starts at order lambda. Okay, and we are treating lambda to be small. So you have a series here which you know how to sum, and this is what? This is 1 over 1 minus, okay, I have a small issue, I should put a minus here. So that's how I define a minus I sigma. Okay, so this is minus I sigma. That's minus I, that's minus I. So that gives you minus of minus I sigma minus q square times, and I have missed a factor of I also here, okay, that's the sum of the series. Okay, let's see, minus times minus, that gives plus, and I times I gives minus 1. I square is minus 1. So I get an overall minus sign here, and you have this factor. So these two cancel. Okay, and you get I over q square minus m square plus I epsilon. I am multiplying this factor here, and then you get a minus. Okay, this plus epsilon I will write at the end. You get minus sigma of q square plus I epsilon. Okay, now you see why I had kept. Okay, this is fine. Don't need to do anything more. So you see, if sigma q square gives you a positive contribution, then the way we have arranged everything by including a minus I here, we get a positive contribution to the mass. Okay, the shift in the mass or the physical mass is related to this bare mass by a positive shift if sigma of q square is positive. And that's the reason behind choosing those factors of minus I in front of sigma q square, but you don't have to. You can keep it to be plus I also. Okay, so that's the structure of G tilde 2 of Q. And now we have, so yeah, this is fine. Now we told that that there is a pole in this propagator in this 2-point function. This is also called sometimes as propagator. Okay, so one calls this 2-point function also as a propagator. Okay, so if you look at the propagator, it has got a pole at the physical mass. Okay, or equivalently, if you look at the denominator, it has a 0 at physical mass mp. So let's use that information and say that when q square is mp square, the denominator vanishes. Okay, meaning mp, I should write it on the next page, meaning mp square minus m square okay. Why? Because this has a pole at physical mass. Okay, so I have just put q square equal to mp square in this in the previous expression here in the denominator, and then I get this condition. Okay, and with the help of this I can determine physical mass and also the factor of z to whatever accuracy I require. Okay, so let's do that exercise. So I'll write mp square is equal to m square plus sigma as a function of mp square. It says that the physical mass to the lowest order in lambda is same as the bare mass. Okay, they are equal. And the correction starts at order lambda because sigma starts at order lambda. Okay, so that's the correction. Now what I'll do is I will iterate it, and in here for mp square I will put m square plus sigma mp square. Okay, so I can write sigma mp square as sigma of, so here I am writing m square plus or I can do something else. That of course I can do, but I want to do something else. Let's take sigma q square. Okay, and expand it around, do a Taylor expansion around mp square. No, around m square. So I will have sigma of m square plus q square minus m square which gives sigma of mp square as sigma of m square plus mp square minus m square sigma prime m square. Okay, and of course you have other terms as well, higher order terms. So when I take this result and put in here, I get physical mass square is equal to m square plus sigma of m square plus mp square minus m square okay. Now you see this term is of order lambda, right, because sigma starts at order lambda because this is the first diagram it has. Okay. Now what is mp square minus m square? If you take m square that side, mp square minus m square starts at order lambda. So mp square minus m square is a order lambda term. What is sigma prime m square? That's a derivative of this, and this starts at order lambda. So that derivative, this sigma prime is also order lambda term. So this is order lambda square. Okay. So this way you can proceed and find out what is the physical mass in terms of as a function of m and lambda. Okay, and this is a perturbation series in lambda. So this is how you can figure out what is the physical mass, and to order lambda, mp square is m square plus sigma m square. So all you have to do is look at the one particle irreducible function in irreducible diagram, okay, calculate its lowest order, and that gives you the shift in the mass, the shift, and that shift together with the m square gives you the physical mass square. Okay, good. So the next question will be how to obtain z, okay, as a function in perturbation theory. So now I know how to get the physical mass in perturbation theory, at least to order lambda. I can keep iterating this and get higher order terms as well. Okay, but let's look at the Z factor. So here you see that the claim is that if you look at 2-point function, then it has a pole at the physical mass, okay, and the residue at this pole is Z, right, because that's the residue. It's I times Z, but I will not say I times Z, I will just say Z, okay. So the residue is Z or I times Z. So let's find out Z from the perturbation theory. That's what we want to do. So finding the residue of the pole in perturbation theory. Okay, so what do we have? We have, this is the propagator or the 2-point function. Remember, this is also called as propagator in an interacting theory. This is also referred to as propagator. So what's the residue? So let's look at the denominator. Q square minus m square minus sigma q square. Okay, because we are looking at the 0 of this, I will not worry about I epsilon. That's not relevant now. So what is this? This I can write as q square minus, what is m square? M square, we have seen that it's mp square should have been mp square minus sigma of mp square, right, because to the lowest order m square is same as mp square. So m square is mp square minus sigma mp square. Okay, that's what I want to write. Okay, that is what your m square is, and then minus, and I do an expansion around mp square, physical mass. Okay, I should have done something else, but nevertheless, let's proceed with this because it's perturbation theory, it will not matter, at least to this order. So this cancels and we have q square minus mp square, that's what I take common, and I get 1 minus sigma prime mp square. Okay, this is to the lowest order. Is that fine? 1 minus sigma prime evaluated at mp square. Okay, that's fine. So what have I obtained? I have obtained that to the to order lambda, this is same as I over q square minus m physical square times 1 over 1 minus sigma prime of mp square which is 1 plus sigma prime of mp square. Okay, because I put in the numerator and we are doing a perturbation in lambda. Okay, so you see that, I mean, of course, and there are other terms. So you see that you can obtain Z if you calculate sigma and take a derivative and evaluate it at q square equal to mp square, which is same as, to the lowest order it is 1 plus sigma prime m square. Okay, so this is a function of lambda and m. Okay, so we can figure out what the residue is from perturbation theory. Okay, I want to make a remark here. And the remark is the following. So, so let's look at this. This is in free theory. Okay. And what is this? This is G2 XX prime. An interacting theory, you have this object, okay, which we denote again by the same symbol. And here, if you write this in terms of G tilde, I should write Q now. Okay, Q dot x minus x prime Q, then you know what that G tilde 2 of Q is. Okay, in this free theory, G tilde 2 of Q is I over Q square minus M square plus I epsilon. Okay, and remember in free theory, M square is the physical mass. Okay, but if you do the same thing here, okay, I'm being a bit okay, let's proceed. Okay, here the leading behavior is near the when Q square is near mass shell, then the leading behavior is this, and let me denote that by this vector. Okay, now of course there are other terms. Now what you can do is, if you redefine the fields here, see, the normalization of fields is not fixed. You can choose to normalize it differently, right? So if I take, instead of phi, I take phi r as the fields, okay, and multiply a factor of z here, or rather square root of z. Then what happens? Then if you do the same thing, on this correlation function will be okay, which is just z times the original correlation function in terms of these phi r fields. And now if you calculate G tilde 2 with this normalization of fields, then your G tilde 2 will not involve z, right? Because you have got a z here and that z will cancel. Okay, so you see that you can get rid of z by choosing a different normalization of the fields, and that is why this factor of z is also called field strength renormalization. So here, let me write first this answer. Then for this case, if you calculate G tilde 2 of Q, then its leading behavior will be I over Q square minus M physical square plus epsilon without a factor of Z, plus other terms. Okay, and that Z disappears because I have changed the normalization of the field. Okay, and that is why Z is called field strength renormalization. and sometimes you also add constant. Okay, or renormalization constant, or field strength renormalization constant. Okay, we'll stop here and see you in the next video.